So we know that giving masses to neutrinos, you can give them via direct mass, which is I think interesting. The main question that we address here is how to give masses to left negative. So of course you are not seeing nu r, so we don't care how to give masses. So we mass to left-handed if direct mass, yes, but to give Maharata mass, you don't need a nu r. It's not necessary to have a nu. So we will see many types of models. Some of which will require nu r, some of which will not require. So we will see one. But what we will do is this type. So we will look at what are called as seesaw mechanisms, which is the most popular ways of giving mass to neutrinos. I will go through this in detail, and then I will go through what are called relative mass models and some other mass models just in short to give you an overview of what it means to give neutrino mass, what are the things that people have done over the years. Okay. I mean, only talking about people make their life looking at mass matrices and mass models. It's not something that I can summarize in 1 hour. So I am just going to do the seesaw mechanisms in somewhat detail because they are the most important and most talked about, and everyone should know what they are. And other ones I will just mention what the techniques are. So it's good to have an idea of. So first thing we will do is the following. So now that we know that direct mass is allowed, and we know that Maharata mass is allowed for nu r, so that's given to us. So we accept that electron number is valid. Then what do we have? So we have this direct mass term, which was this minus phi d L bar phi c nu r solution conjugate. After you break electronic symmetry, this phi d times this wave of phi, they give rise to this m d. So we have the direct mass. M d nu L bar nu r plus solution conjugate. Which conjugate is just nu r bar nu L. So this is something. Next we know that nu r can have another mass, and this we write as the following: is minus half m r, right? Nu r c bar nu r plus summation. If at all left-handed neutrino get a Maharata mass, it will look like this: minus half ml nu l bar nu l plus summation. It doesn't matter. I mean, nu r c bar nu r, the summation conjugate would be nu r bar nu r c. And here I wrote nu l bar nu l c. So although these two look the same, they are the same. The summation conjugate comes here and the summation conjugate comes here. So both are exactly identical. So to get this ml, we need some physics. We understand it. Okay, so that's what we are doing. But let's not introduce standard model things first. Let's just start by assuming that only thing we have is nu r. Still, standard model, but something very minimal. So let's just add nu r and see what are the consequences. Because till now we did not really discuss things together. So we said nu r gets Maharata mass. We said if nu r is there, then nu l can have direct mass. But now let's take everything together. Once you have nu r, you have to have direct mass and the Maharata. So let's see what happens when we add both of them. Okay, so what happens? This is a direct mass. Okay, so once you add nu r, you are going to have this direct term. So this is direct term. This is also direct term. But this involves conjugate particles. So they would actually come in your conjugate particle. This term is the Maharata term for nu r. So this nu r c bar. So this is Second term. Second term. Okay. Let's try to see whether. So what is the Dirac mass term? The Dirac mass term is, so I'll just write MD mu n bar mu r minus 15. Now let's try to see, and let me write a term. Let me write a term that I have here, and then let's see how. So I have written this term as mu r c bar mu l c. So let's see what that term actually is. So I have mu r c bar. Okay. So what is this term? We don't write mu r c bar. Don't write mu r c bar. Because unless I am mistaken, there was a minus sign. Then there was mu r transpose C times. What is mu L C? Mu L C is simply C times mu L bar transpose. Now C diagonal C is 1. Okay. So this is minus mu r transpose mu L bar transpose. Okay. Now these two are fermions. When I interchange my fermions, I always get a minus sign. Okay, because they are fermionic fields. So if I want to bring my mu L to this side, see these are transposes. I want to take out transposes. Okay. So, and this is a number. So this is, so transposing is the same. Okay. So I transpose this. By transposing this, I have to take mu L on this side and mu R on the other side. So that gives me a minus sign. That makes this side as plus and gives me this is mu L bar. This is the only thing that we are not normally used to. Interchanging of fermions should always give you minus sign. Because fermions will be anti-completion. So now what has happened? This means that mu r c bar mu L C is essentially equal to mu L bar mu R.
Should there be part of the efficient term?
This is half of it. So actually what I have done is I have taken minus md mu L bar mu R, and for the sake of future convenience, I split this thing into minus half md mu L bar mu R and minus half md mu R c bar. So they are the same formation. So Dirac term is broken into two parts. My other term is the way it is. It always has a half factor because of this half factor is all Marana. The reason why I separated this Dirac term into two parts is the following. This I can write in this form. So you can check quickly for yourself that indeed the multiplication of these three matrices is equal to these three terms. So what this means is if I choose my basis as mu L and mu R C, choose my basis as mu L C and mu R, then my mass matrix is a 2 by 2 matrix. It has 0 here because mu L mu L C term is 0. I have not given any Majorana mass to the trinity. These both of these are empty. Okay. So it's a symmetric matrix. Both of them have to be empty because they came from the same term. So it is empty. This part here is MR, where this capital A and small m are the same. So this MR. So that's it. So we have this matrix now, which tells you about the mass of mu L and mu R, okay, or mu L C and mu R. However, it's not a diagonal matrix, it's a mixed matrix. So we do what we naturally do. We see if we got a particular. So we diagonalize this and see what happens. So what this means is there's some direct masses, some marginal masses, and it's not clear what things are. So let's diagonalize things and see what happens.
Capital.
No, it's the same. It's tiny. Capital. Okay, so can be the mixing element. MD is much smaller than MD. So let's take this. So tan to theta is 2MD by M. So tan theta is MD by M. So mixing angle is very small. What about mass eigenstates? So 2 by 2 is below the trace. So look at a trace. Trace should not change. Then you look at determinant. Determinant should not change. Usually these two give you the mass eigenstates even without it. So the sum is trace is MR. So sum should be near the MR. Determinant is minus MD square. So you can solve that. And in the approximation that MD is most of the MR, I'll give you those answers. So M1, the first eigenstate, eigenvalue, turns out to be minus MD square by MR. The second eigenvalue turns out to be MR plus MD square. But this term is much smaller as well. So two eigenvalues are this, 1 and 2. Mixing angle is this, theta, which is MD by. So now, look at these two eigenvalues. See, this M2 is like MR. MR is very heavy. So when you think of MR, think about 10 power 10 GeV or more. So, very high. When you think about MD, think about GeVs. It's like masses of all other quarks and leptons. So MD is much smaller than MR. So MD square by MR is very small. So if you look at the second term, which is MR plus MD square by MR, you can essentially neglect it. Now look at the first term, it's minus MD square by MR. So let's see how much that comes out. Okay. So we want to calculate MD square by MR. Let's put some typical value. So MD, okay, let's say you want it to be G. G. So this is G. Okay, no, G times MR. I said typically you take it to be 10 power 12 G. Let's take 10 power 12 G. G. So how much is this? It's 10 power so minus 10 GeV, which is so what has happened now? We had our MD, which actually took it to be just like quarks and leptons. Okay? So we don't have to introduce anything new to it. Just like Higgs, left-handed lepton, right-handed lepton. And that is observed of G. You can take 10 GeV, 100 GeV. Then we had this MR, which we said is no more than 10 power 10 GeV. It can be 11, 12 or 10. But because of this MD square by MR term, the final mass that we got was very small altogether. So what's happening now is, when we only had MD, only direct mass, our problem was that Yukawa coupling was 10 power minus 11, 10 power minus 12, and we didn't want it. That looked very aggressive. Now, the masses that are involved in the problem are large masses. So there is nothing new in having MD of the order of GeV because we know all the quarks and electron, I won't have mass of the order of GeV. So that's not a big deal. This MR also I said that you can have the mass. The MR is not restricted. It can be anything, even as high as cancer. So even this can be a large mass. And then this cancellation can actually make this thing to be good quantum. Again, another thing to notice is we don't know what MR is at this point. But you can imagine that if MR actually goes up, the neutrino mass goes down. So this I call as M1. So MR goes up implies that M1 goes down. So this is the reason why it's called a seesaw. So let's say you want to match this scale M1 equal to quantum electrons. So what will you do? If you know what is MD, if you want to decrease M1, you will just increase your MR. You say that my Majorana mass for nu R is not 10 power 10 but not 10 power 12. So instead of GeV, if I write it as 10 GeV, so I can make it 10 GeV times 10 GeV, but I'll make it 10 power 12 GeV in the denominator. So cancellation is the same, I get quantum electrons. So increasing the mass of nu R, I decrease the mass of my neutrino. So this is a seesaw. So all models which do that are called as seesaw models. So what has happened is somehow automatically, without doing anything, see, all I did today was put in nu R and nothing else. Okay. Just by putting in nu R, I got a very small mass for neutrino, okay, without having to do any check derivative. So that's why the seesaw mechanism came from.
So you're saying that since MR is a Majorana coupling term, it can be a totally different order from U power. That's why we can let it be whatever.
So M1 therefore is 0.1 electron volts and MR is 10 power 10 GeV. So which is exactly what we saw sometime back. So therefore, instead of writing MR plus MD square by MR, I can write this just as MR. Okay, because this is electron volt and this is 10 power 12 GeV. So actually I got two neutrinos. One is very light neutrino, which was light electron tau neutrino. One is a very heavy neutrino, this M2. This is a very heavy mass, 10 power 12 GeV. So therefore, we have no hope of seeing it at all. If at all, it may have some effect in early universe, but at lab energies, you won't be able to see. What we'll be able to see is this M1. The next question. Now here we have Dirac mass and Majorana mass. So this M1 has a mass whatever, M Dirac squared over M1. So question, is this mass a Dirac mass or a Majorana mass? Or is it half Dirac and half Majorana? We know they are different, right? Because we know that in double beta decay neutronous experiment, we see only Majorana mass. Dirac mass will be the same.
So M1 is the mass of some particles, neither Majorana nor beta.
So what is the Majorana particle? It's a particle which is its own antiparticle. What do you mean by particle which is neither Majorana nor Dirac? There is no such particle. Either you are Majorana or you are Dirac. You can't be both. Combination of quantum state. Simple condition. The definitions are very different, right? You can't be both Majorana and Dirac. You can be only one of only one, either Dirac or Majorana. Okay. So no superposition of particles. Different definitions. Right? Either there is a Majorana term for you, or there is not a Majorana term. You can have a Majorana term with smaller coefficient. It's a Majorana term. Once you have a Majorana term, you have a Majorana particle. So let's see what it is. So let's go to this new basis. The basis is the basis which diagonalizes this. So this new basis is this nu L and nu RC. the new basis is u1L and u2L. Okay, and you rotate that by this angle theta. So we know what angle theta is, we know what angle value is. So let's write down the Lagrange change in that basis. So what does it become? The basis is u1C and u2L. This is u1L bar and u2L C bar. Okay. u2L bar, sorry, not C. So this was the definition. New basis is u1L and u2L. Okay, there is no obvious one. The matrix is diagonal M1 and M2, and therefore Lagrange becomes equal to this. So I expand Lagrange. Lagrange looks like this. So now you can look at this Lagrangian, and now you can tell me which particles are Dirac and which are Majorana. Both the terms look like Majorana mass. So what we obtained is we obtained two neutrinos, U1 and U2, both of which are Majorana. So what did we do? We started with one Dirac neutrino. We had one Majorana neutrino, nu R, okay, but they mixed because they had a Dirac. Finally, what we got was two neutrinos, both of which are Majorana neutrino. So even this U1, which is lighter neutrino, is a Majorana neutrino. And this nu2, which is heavier one, is also Majorana. Okay, so it's like this. Majorana neutrinos means lepton number is violated. Once it is violated, everything is Majorana. You can't have only Dirac. So once in your theory you introduce lepton number violation, it propagates everywhere, whatever means happening. So then everything can have Majorana, all the neutrinos. So that's why I said Majorana doesn't take Dirac alone, it converts everything to Majorana. So you have two neutrinos here, both are Majorana, u1L and u2L. And therefore even nu-L now get a Majorana. So we did not start by giving Majorana mass to our neutrinos, light ones, nu-L. It turns out that they get induced Majorana mass because nu-R had Majorana mass already. So you can't escape from this. So neutrinos do get Majorana. Therefore, when you do the experiment like double beta decay, neutrino-less experiment, okay, we will find neutrino mass as long as it is there, as long as it is Majorana. So it's also a test for Majorana mass of nu bar. So this becomes general prediction of lepton number. The nu-L did not have Majorana mass specially given. It's okay if it gets induced through this. It will still give rise to the neutrino generation. So induced Majorana is gone. So this is how you can induce Majorana mass. Whatever I told you now.
So once you get the ABD, how do you know whether it was induced or whether it was, like we could write the L itself as a Majorana particle?
So what you do is, you know, as I showed yesterday, the decay rate of this in terms of the Majorana mass. So if there is some other way for you to measure that, then you can determine the rate. So you need to. A priori, I will come to it in detail when I talk about this after this experiment. But the results have to be interpreted carefully. There are many other ways by which you can get double beta decay. But we will be further. So what has happened? This is a mechanism. We have a light neutrino which has a mass of md square by m. Actually the mass was minus md square by m. Okay. So why did I sweep it under the rug? I can have so I got a mass as minus of something. So what would that mean? So why does this not trouble me? Why does this not trouble me?
Is a sign of your
No, this thing is positive. One also has to be positive.
yeah.
See this mu will enter the Lagrangian, okay, like mu psi bar. Nu L bar. Okay. But no, I can change the phase of nu L. See, this is after electric symmetry. So phase change with respect to charge and all. So I can in principle change the phase of this nu L bar and the phase of this nu L and get it. This is normal true of fermions. Fermions can have the masses of fermions. It can in general be positive, negative, complex, whatever, because the phase of fermion can be changed. In general, you can change the phases of fermions without affecting the identity. This is the standard. Okay, so therefore, even if you get negative masses, you don't care. You say, okay, I change the masses of fermions and I absorb them, make them whatever. So this is the magnitude point. So yeah, so light chose get a mass. For GV, MD and MR of 10.9 GV, my MD was 10.1, this was something like that, and we get a light emission. So these are generally characteristics of seesaw mechanics. So let me go through that in slightly more detail. So how does that happen? So what we saw till now is what is called a type 1 seesaw. It's type 1 because it was the first discovered seesaw. So what does this mean? So let's see, what we saw now was diagonalizing matrices and giving neutrino numbers. But you can look at it in a different way. You can look at it as a Feynman diagram. So you can look at it something like this. So what did we get? So we said that we had a neutrino, we derived this. There was nu L and there was nu R. Okay, so nu R I will just call as N for. So what does this mean? This means that I had this vertex which was phi nu L this was phi, this was nu L, and there was this N, or what we call as nu R. With some coupling. Coupling was given by phi here. Now, this N will also phi. This should have been. It can also couple with this phi L. This is my nu L going in. This is my nu L C coming out. So what is happening now? So if I have a process that looks like this, what I can do is this is equivalent to a nu L coming in, nu L C going out, and everything here I can take it into account. So and I can determine what is the amplitude of this process. Let that be something. But what will that mean? It means that amplitude will be given by something here times nu L C bar, whichever, or nu L bar QC. So if I can have a process like this, effectively this process will give rise to a term that looks like nu L C bar U. Okay, by putting everything here in the block. Okay, you agree with this? In fact, I can even have a diagram that looks like this. I can have a phi here and phi, just like this, some base channel, T channel. I can have a diagram like this. Again, I can put everything here in the block. Let's see, UL coming here and ULC. It is essential for this that this particle N is a Majorana particle, because this UL is coming in. If I look at the electron number, this is NL, but since ULC goes out, what I should have here is NC. So therefore, this has to be another particle. So as long as I have another particle going like this amplitude is equivalent to saying that I get induced mass moment. So this is the so-called type 1 seismic. We can see what the induced mass is. So this is YD. Okay. So what is the induced mass? There is this YD. Then if you are at once, so this propagator is 1 by E slash minus Mn. And then this vertex is again equal to YD. And then we have this phi going out. So the phi, there is a phi coming in. So here I have a R going out YD, then I should have phi, and here I must have phi going out. So what has happened effectively? I got external X, so let these go out of the block. So externally I got a new L, which is external particle, a new LC, which is external. There is a phi, which is external, phi, which is external. Internally I have a propagator, which I write as 1 by E slash minus L. This is, I'm just writing down the amplitude for this process. Okay. Now, this particle is very heavy, 10 power 12 G. We are doing experiments at very low energy. We measure mass of neutrino at energies of maybe keV. Double kinetic is done at MeV. Okay. So, P slash is always much smaller than MN. You can even neglect that. And then what we can write this thing as is pi d square divided by Mn times, so there is some ULC bar phi transpose on top. There will be something in front because face space blah blah blah. So just be not very. But then what's important is I get YD square over Mn and a ULC bar phi transpose UL. We never wrote something like this because we always said that we want a term in the Lagrangian that has dimension not more than 4. This is a term. What is the dimension of this term? Only this part. This is dimension 5 term. Of course, to compensate for that, I have got this 1 over Mn. So what this means is that I have an effective Lagrangian, which goes as some constant, some YD squared here, times something which is neutrino or LL phi in some combination divided by M. So this is dimension 5, M is dimension 1. So Lagrangian has dimension equal to 4. So that is fine. So this is what I have written. Effective Lagrangian looks like pi d square by mn times such a combination. Okay. Depending on what are the combinations of Feynman rules inside, I will say this is LC bar, LL, 5 and 5. Okay. And what will happen to this effective Hamiltonian? It will be some combination of whether I can have LC bar times L or LC bar times 5 and so on. What I have done is just call this A, B, C, D and multiply by some coefficient which I call as kappa. It only means that I have a product of these 4, but I can take in whichever way I like. Normally, this is written as this. It's written as kappa 5 times L, 5, 5. It's just a shorthand for writing. But what kappa 5, L, 5, 5 actually means is the following. So, I have kappa 5, L, 5, 5. What it actually means is that we have got this LL, which is the same as LLC bar. We have got this. Then we have got another LL. Then we have a 5 and we have 5. So we have 4 fields. L, LC, 5 and 5. Okay. And depending on we didn't calculate this thing exactly yet. So depending on what the vertices are, okay, in some other cases vertices can have some gamma mu, sigma mu, lambda, which would mean that the way these are combined would change because you can have different combinations. So then the way to write this is there are some ABCD indices and there is a coefficient kappa ABCD which depends on what it is. So this depends on this part. So it depends on A, B, C, D and depends on Feynman. Depends on Feynman rules means depends on the mechanism, model using Feynman. So for this case, which was type 1 seesaw, the Feynman rules were simple. So this was just pi d square by mn. So this kappa ABCD would simply be equal to pi d square. But I wrote it in this form. As we'll see later, there are many seesaw mechanisms, all of which use the same Feynman form. So this is what we get for type 1 seesaw. If we put that in front of I plus 4. So this is how your neutrinos will get passed through seesaw mechanism. So what did I have here? I had only one new arc which propagated. This is a singlet under SU2 plus U. Now phi is SU2 doublet. Nu is SU2 doublet. So L. So therefore, if I combine doublet and doublet, what do I get? So I am now trying to look at something like this. This is a phi, and this is the this is SU2 doublet. Spin up part. This is SU2 doublet. So when I combine them, what should I get? It's like combining spin half and spin half particles. So I get a spin 0 particle and I get a spin 1 particle. What we did right now, where this was N, it was like getting a spin 0 particle, it's a singlet particle. Right? So N was the SU2 singlet. But now it may be possible to get SU2 triplet also, which is like akin to a spin one part. So it's possible to get not N but what is normally called as sigma, which is a SU2 triplet. So you can choose not to put in this new R at all. Say I don't need new R in it. I only want this sigma. So it's your choice. It's your one. Once you introduce this, then just like before, one can have a diagram like this. So phi and N, sigma, phi, and L. Again, the outside legs are ln, ln c bar, phi, phi. And internally there are some couplings here. Triplet means slightly complicated couplings because you get polymatrices and so on. But we know that we can write something which is an effective. So therefore, exactly what I did here on my type 1 system, I can do it by replacing this diagram, earlier diagram which had N here, by a sigma. And what I get will be exactly identical except for this kappa ABCD will change. It will be something much more messier than what we had earlier. But it will be something, it will be some constant. Right now we don't need to care what a constant is. The only thing to note is that we can have a mass for nu L, because once you put this thing in block, you still get a mass for nu L, right? So you get something which is ln c bar ln. After symmetry breaking, these phi becomes just equal to v, so there is some v square, and there will be something complicated here. So this kappa, this sigma as a propagator, which is 1 by p slash minus n sigma, which is just equal to n sigma, because p slash is not small. So this is possible. So again, what you have done, instead of putting in this new r, you put in this sigma, which was a triplet particle, and what you got is exactly identical thing. So now we get y sigma. Maybe let me see if I can draw the diagrams here. This is phi, this is L, this becomes sigma, phi, C going out, and then I can get something like this. This can be phi, this can be sigma, this can be C going out, this can be. So if I calculate this coupling is some y sigma, and then I get y sigma square divided by n sigma, and now it's a triplet, so these terms change, so let's not worry about it now. We haven't really gone into details of SU2, but once you have SU2 triplets, this is how things combine. So there is a this L and phi get combined with this tau vector, which is sigma sigma. Okay, we are not going to go into that. The net lesson is that whatever happens here, finally you see something that looks like a k phi, kappa phi, which is a coupling with dimension 1 over m, times L phi. So that's why this is also called a seesaw mechanism, because you have 1 over m. So if you make this sigma heavier, Neutrino mass becomes that. So this is called type 3 seesaw. Okay, I skip 2. I skip 2 because 1 and 3 are very similar. It's called type 3 because of historical reasons. Okay, first seesaw which was discovered is called 1, second was 2, and so on. We'll come to 2. This is like 3 seesaws. One would ask the question, well, if you had this nice new R mechanism already, why did you want this type theater? Okay, so the answer will come. One is that it's possible that there is no new R. Secondly, it turns out that this mechanism is easily testable at experiments, like LHC. If there is new R is not. So I'll come to that in a bit. So, but I can just take it as in principle, I show you 2 mechanisms, one with new R and one with sigma. Right, so here's what is slightly. Now let's look at what is called type 2 seesaws. It's a slightly different philosophy. So we know that you cannot have a term like UL C because SU to U1 it was already. That's why UL could not have higher. So what is this? If you had LL bar LLC, which is so LL is 2 1, so doublet under SU2 hypercharge 1. LLC is 2 1. LL bar is also 2 1. Same hypercharge. So if I combine them, I actually get again spin. So hypercharge 1 plus 1 is 2, and then doublet means spin half gives you spin 0 spin 1. So either it gives you a singlet or it gives you a triplet. Okay. So this or this. So if I only want to write a term which is LL bar and LLC, it will be forbidden. I cannot just write M times this. However, what I do now is I add another particle to this, which is, let's say, a triplet here and a hypercharge equal to -2. So what am I doing? I want a term that looks like LL bar, LLC, and something. This should be inherent at SU2 and U1. I know that if I do an LL and LLC and LL bar LLC, combine them, I get this is 2 1 combined with 1, so doublet and hypercharge 1. This gives me a singlet with hypercharge 2 and a triplet with hypercharge 2. So what do I want? I want to make a singlet out of these 3 combined. So one way out is I introduce a particle which I call as delta. This delta, I'll also make it a triplet, so spin 1. And I give it hypercharge equal to -2. If I have such a particle, then these 2 can combine. If I combine them properly, this spin 1 particle and this spin 1 particle, this gives me a spin 0 particle. So I get a singlet. And I have hypercharge 2, hypercharge -2, and I get a 0. Now this can go to Lagrangian delay. Okay, so therefore, this can go to Lagrangian. This is right now I'm just playing. So I told you that I can do this with it. So then I do slightly more. Then I do the Feynman diagram. So I have this LL bar, LLC delta.
What would the singlets do?
Let me do the delta first. Then I will. So now what I got? So I got what is LL bar, LLC, and delta. So I can draw a Feynman diagram which looks like LL coming in, LLC going out. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introducing this term is I have said that it is an interaction that looks like this. So what I have done by introduc Now let's see what is delta. What was delta? It was a triplet in SU2 and hypercharge was -2. So this is a triplet, so there should be 3 particles. What should be the charges? You have all the information. So I told you there is a triplet, so there are 3 particles. Tell me why. Tell me why also. The charges, and I need to know why they have this. How do you find the charge of a particle? So Q is equal to T3 plus Y by 2. Okay. So what is T3 of the particle? 1. So that should be plus 1, 0, 1, minus 1. And Y by 2 is minus 1. Okay. So my Q becomes 0, minus 1, minus 2. So this delta should be 3 particles from a triplet. Delta 0, delta minus 1, delta minus 2. Should have negatively charged particle and double negatively charged. This is called as Higgs triplet. We can see why it is called Higgs triplet. When it's a scalar particle, it has to be scalar, right? Because it's LL bar LLC, so dimension 1 particle actually goes up. Okay. And I put it as a scalar particle. So now what happens? If I got these 3, then I can break symmetry, electrostatic symmetry, electric symmetry breaking. Scalar particles can undergo electric symmetry breaking. They can have different ways. Now which of these 3 can get a vacuum expansion value? Only the first one. Vacuum should not break charge energy. That should be constant, right? If only delta gets a vacuum expansion. Okay, so we will call it wave of delta. So this gets vacuum expansion value. It is up, down, 0 in this situation. So now what happens? This means that if I want to write down this effective term, this is now looking exactly like LL bar LLC. And we have a coefficient here. The coefficient is going to be equal to this coupling, which I call as F, and wave of delta. It's exactly like Higgs. So remember, if it was a Higgs, what was the Higgs term? Higgs thing is at phi, then I get some QR, QL, and the mass term is QL bar QR, coupling constant, which is Y, and wave of Higgs. So it's direct mass term. I got exactly very similar thing, except that instead of QR, I write LLC. So this is the mass term. So what has happened? The neutrino therefore has got a mass equal to F times wave of delta. So mass of neutrino is F times wave of delta. Okay. Sometimes there is a factor of root 2 particulation. So what we have done is we have found one more mechanism of giving neutrino mass. This is called as type 2 system. I have told you only half of type 2 system. Let's at least wait here and see that we are agreeing. All I have done is added this extra interaction called LL bar LLC. This is what I have done. So I add a Higgs triplet delta, which is delta 0, delta minus, delta minus minus. Then Lagrangian, I get the term that looks like this, minus f mu L bar tau dot delta times 2L. It's a triplet, so the term will have a tau dot delta here. This is again is to algebra. I wrote here only as mu L bar mu L C, but it can be NL bar or NL C. So actually, to be precise, when I say this is the mass of neutrino, it also will give the similar mass term for electron. So it will also give you electron mass term as almost exactly the same times. Except that this gets added to the original electron mass term, which is already very high. So therefore, this is high. But this mechanism will mass to go to line. So I had told you about this term, right? Not about that. So this term is possible, and this will be a mass which is equal to f times wave of delta 0. Okay. And root 2 depends on what definition of delta 0. So Feynman diagram we saw already. It was basically like L coming in, C going out. And then I get this. This is how we got a mass equal to f times. Now the subtlety which I just wanted to mention. Subtlety is that once you introduce this delta, you also get a term that looks like this. Because just like u and u form a triplet, even phi and phi form a triplet. Because phi is also 2 minus 1. Not minus 1. 2 1. So what happens is this phi, where phi is also 2 1 2 1. They also form a triplet with hypercharge 2. And therefore I can have term which is phi phi delta, where delta is 3 and minus 2, such that this term exists. What this means is that there is a vertex that looks like phi delta. So such a term exists. Now we think about our old seesaw mechanisms. What did we have? L phi outside. Right? Now you can imagine that this delta can now combine with because there is also coupling which is L, LC and delta. So now what have we done? What we have done is write down this type 2 in the format similar to the earlier type 1 and type 3. So again we have got phi L on the outside. Earlier we used to have this Mn or M sigma, but now we have got this delta. So what happens if I draw this Feynman diagram? I will get, so here I get, let's say L phi. I won't go into details of the infrastructure, but since I got this delta, this is boson. So property is 1 by T square minus M square. So T square is very small, so M square. And some negative signs that is not there is something. So again what we have got is a dimension phi operator, L phi. Then something that looks like M delta squared. So there is definitely some problem here. Not the same one here, only we have only 1 over M. The reason is that this phi delta has dimension 3. Right? Lagrange instead dimension equal to 4. So the coupling constant should be some mass. So it's mu. So this coupling is mu. This coupling is F. So this is F. It's mu divided by M inverse. So without going into details of triplets and how the sigma matrices mix, this is what you can say already. That I get the effective Lagrangian term, which will be F mu divided by M delta square. But F is the coupling here, mu is coupling here, M delta square is propagated, and again L is phi. Now this constant F mu by N lambda square has a dimension equal to dimension of 1 by M. So I can then write this thing down as some kappa phi by M and scaling phi. So what I have done is I have shown you that even if you do things in a very different way by adding this 6 triplet, finally you seem to get exactly the same thing. So all such mechanisms which boil down to L phi by M are called as seesaw-like. So in general, this term is applied to all such mechanisms which give you an effective Lagrangian thing going as kappa phi divided by M times L phi. That's the seesaw-like. And these are 3 ways of getting it. Type 1 was when your intermediate state was mu r. Type 2 when you had this sigma. I'm sorry, type 3 when you had the sigma. And type 2 when you had this delta. So these are the 3 sort of main seesaw mechanisms. We will come to other questions. Other questions, I don't have a singlet. So try that and you will see that it doesn't give a master. Okay, you can, so here for example, this was 1, 2 plus 3, 2. We added this 3 minus 2 and we got something. We could also add 1 minus 2. So go ahead and have something which is called x, make L bar L C x kind of term and see what it gives. If a term does not give you in mass term, the term should look like so mass term should look like Neutrino, let's say. So it should look like mu L bar mu L C times something. If you don't get such a term, then even by Lagrangian having something else is not a function. So this is exactly what I have here. Assignment diagram. Let me try to draw one of the bottom. So this is phi delta. So this is summary of this. So whichever way we wrote things down, okay, this is a singlet, so therefore this is L phi and phi dagger L. This was triplet, so therefore there is down. This is a triplet, so therefore there is so. So type 1 seesaw, L and phi combined to make a singlet, okay, because we had this vertex which was phi, L and N, right? So therefore L and phi make a singlet. Therefore the grouping. Here L and phi make a triplet. So therefore we had grouping like this, and a phi, there was a L, and there was a singlet. So L and phi form a triplet. This L and phi form a triplet because there is tau. In type 2, L and L form a triplet. So type 2 therefore looks like this. L with a triplet and phi form a triplet. Because So what these three mechanisms are just different ways of combining L, phi, phi. Make them combine L, phi, phi in whichever ways you want. Each way will give you some possible value. These three are the ones that I want. So these three have different first lines. First line will be very different. Just yd square and some combination, y sigma square and something that is tau, just some mu by m delta square, something which is tau. Now if you look at a second line, all of them have the same second line. So what this means is that effectively the kind of mass that they will give will be the same. So if you do not see n, or if you do not see sigma, or you do not see delta, you will not be able to distinguish between the three mechanisms. So at lab energies, all these three mechanisms give you exactly the same predictions. There is no change at all. So tomorrow, if you want to identify which of these is the right mechanism, you have to be able to identify in the lab. You either see an n, or you see a sigma, or you see a delta. So that is sort of the goal of next generation experiment. So if you find one of these, then you know what is the mass mechanism. If you don't see them, you can't distinguish. So this is what we know about them right now through experiments. But we don't know which of them is true. Type 1 seesaw is very difficult to see in that. This is the following. See, we saw that if n g, then you cannot see it. So you can't produce it. You don't have central mass energy of 10 g. So it's not possible. Okay. What happens when n is light? So let's say I tell you that I have this new arc which has Majorana mass of T. Why not? What's talking about it? Okay. So this is what. So type 1, and I have my Majorana mass equal to T. So why can't I see it? Why cannot I see it at let's see for example. The reason is the following. You want to produce this particle in the lab. How will you produce it? You want to collide something and produce it. In principle. So what will you collide to get n? If you are allowed to make any particle you want, how will you make n? You have to have some interaction with n. So what is the only interaction you have with n? N and Higgs. You have only one vertex with n. No, n has only this interaction. N, phi, and n. That's all we know. It has no other interaction. So if you want to produce n, you have to collide n and phi by some means. And what is this coupling constant? This is what we call as phi. So now if you want to produce this n, the rate of production, so gamma of n phi going to n is going to be proportional to pi d square. Now what is yd? We know that mass of neutrino that you get, what is that? So you see some mechanism. Md square by mn. So Md square is yd square times v square by 2 times mn. So let me write down this again. Mu equals 5t squared t squared by 2 times. So let's see what is yd. So yd squared is equal to, what will happen? 2 mu mn divided by d squared. So let's see. 2 is what? So 2 mu is point on the electron volts. Okay, so let's say point on the electron volts. Mn, let's say TeV. So TeV is 10 power 12 electrons. And V square is so V is 10 power 9, 10 power 11. So it's 10 power 22. So this is something like 10 power minus 11. So if Mn is TeV, implies yd square is 10 power minus 11. So which means decay rate of L5 going to N goes as 10 power minus 11. This was yd square, which is very small. So if N is very light, TeV scale, in principle you can produce it, but the cross section is very small, 10 power minus 11. So that's the reason you can't produce it. So you lose both ways. If it is heavy, see if Mn is heavy, yd square will be larger. Right? So if Mn is 10 power 12 GeV, then here I would have something like 10 to the power 21 also. And then yd is there. So this is.
But here V is also this V. This V is not the same. Here V is also controlled.
He is very much no. You know, be very accurate. 246 GeV.
That's the same V. How can we say that's the same V? Yes. Here.
Because this is the same Higgs, no? This interaction. This is the same Higgs. Okay. The interaction was with Higgs. Coupling is yd. So V is the V of this Higgs. So that has to be valid. So therefore, in Mn you lose both ways. Okay. So if mass is very high, then yd square which was 2 mu times Mn divided by V square, that can be high. So this can be 2 times 0.1. Mn is 10 power 10 GeV, so 10 power 19 electron volts divided by 10 power 20. So this is 10 power minus 4. It's not very high. Minus 4 is not high. So you can have a large coupling constant, but the mass is so heavy that you won't be able to produce it into that. So then they are killed. If the mass is low, TeV mass, then as we saw here, the cross section is proportional to yd square, which is 10 power minus 11. So therefore, although type 1 seesaw looks okay, it is almost impossible to confirm type 1 seesaw. So therefore, this is very hard to establish. Type 3 seesaw, one would think that similar thing applies. In type 3 seesaw, if you have sigma of the order of TeV, then same thing applies. yd square is 10 power minus 11, so it doesn't work. So if you have type 3 seesaw, then if m sigma is equal to TeV, then yd square is 10 power minus 11, and therefore if you want to create that through this phi and L going into sigma, is unobservable. However, the nice thing about sigma is that sigma is, see, n was a singlet. So only interaction it had was with n and phi. Sigma is not a singlet, sigma is a triplet. Therefore, it can have many other interactions. So, for example, what does a triplet with SU2 mean? That it couples with W and Z. So then it can couple with W. It can have a sigma plus here and sigma 0. Sigma is a triplet, right? It's tripartite. Sigma plus sigma 0. You can have W, and making W is not difficult. You can have W simply through two balls. So you want bar, so you can make a UD bar, for example, and make it up. So all you need to do is collide two blocks, you get W. This constant is G. G is not very small. G is not part of 1 by 10. This constant is also G. It's issue to triplets, so complete constants are the same. So now you see the cross section. So this is UD bar going to W, going to sigma plus sigma minus. It is just something like G squared. So it's like 1%, 10%. So it's like G squared by 4, G squared by 4 is alpha, which is of the order of. So what has happened now is sigma is possible to be produced at LHC by just collision of particles, whereas n is not. So if mechanism is type 3 seesaw, it is easy to see at LHC. It may be possible. No one told me that sigma is very right. Okay? It's possible that sigma is still 10.10 GeV. Then I am sorry. However, if sigma is light, it is TeV, you can see it at LHC. If n was light, you could not see it at LHC. But sigma can be seen at LHC. Therefore, people are working hard these days on sigma because it can be produced at LHC through very interactions. Which interactions means bit of levels. Then you have got type 2 seesaw. Type 2 seesaw couplings come from, constants come from very different, because we haven't seen delta, of course. However, this introduces complications in the theory, because we have got this wave of delta 0. Delta 0 is to triplet. So what it means is that it will couple with W and Z, and you know what happens when Higgs couples with W and Z. Higgs gives them masses, Higgs squared. So it turns out that just like you have electroweak symmetry rating for Higgs, you can have electroweak symmetry rating for delta. And this will give extra masses to W and Z. Now we have a very nice prediction for rho. This rho parameter that I talked about earlier. It's NW squared divided by NZ squared cosine squared theta. With only our Higgs, the standard phi Higgs, rho is exactly equal to 1 to first order. But if you introduce new masses to W, new masses to Z, this relation is going to get ruined completely. So therefore, if you put current constraints of measurements of rho, so this rho now gets modified to this. Earlier it was just equal to 1. Now it becomes some 1 plus or some way. So this actually restricts the ratio of wave of delta to wave of phi. So it is indeed still possible to have triplet Higgs and have type 2 seesaw, but we have severe constraints. So I think I should stop here. I will talk about these models briefly when we meet again, perhaps in the first week. So just to summarize, what we saw today is 3 seesaw mechanisms, all of which can give neutrinos mass. and all of them finally correspond to Lagrangian term which is the same. So always do something where you have a term which is n5 divided by n times. People use different conventions. Okay, sometimes they just call this itself as kappa phi and say this kappa phi times n5. So conventions change, differ. As long as you make sure the dimension of kappa phi is such that this is dimension 4. So these happen to be sort of the simplest mechanisms that can be used for us. There are some other ones which are very long briefly. Thursday 5:30.